So, Dr. Clay, thank you for being here for an unofficial second time, officially the first time. It's great to see you.
Yeah, thanks for having me.
So, as a first question, how did movement influence the evolution of intelligence in early organisms? What does this say about the relationship between physical interaction and cognitive complexity?
Basically, every intelligent system that we know of, even the most simple ones that you can think of in early evolution, are moving systems. And intelligence is needed to move. So this kind of developed in order for organisms to be able to move intelligently and survive and figure out how to find food and move to food and remember where they found food eventually. So that's, I would say, the reason that intelligence developed because we needed to figure out movement.
Yeah, and the amount of intelligence kind of predisposes the amount of movement. Is that like proportional?
It's hard to quantify that, but I would say it kind of comes together. Without movement, there's no intelligence, and without intelligence, there's no movement.
Sure.
Um, so I guess, yeah, more intelligent species are the ones that have a lot more options to interact with the environment, like primates and humans with opposable thumbs being able to really dexterously manipulate the environment and do tons of very specific things. Um, but of course, also other species that interact in the environment in different ways have intelligence and do very sophisticated uh, things, action policies.
So how do place and grid cells line up into this as a follow-up question? These are what allow animals to map environments, yes?
Yeah, so these are found in the entorhinal cortex, so a bit of an older structure in the brain that developed before the neocortex. And those structures are classically thought of as like the grid cells were first found in like mice and rat experiments, so rodents that move around in a maze or in an empty room in experiments. And grid cells basically keep track of that space. So they map the environment of the animal, and they can then be used for various tasks, like, for example, for the animal to find food or find back to where it found food before or find back to its home. And that's crucial survival tasks. So the brain developed or evolution developed methods to keep track of space and to be able to also do path integration. So if the mouse took a path, like a very windy path, to find food, it doesn't have to take that backtrace that windy path to get back home. It can take a straight path back home because it has like an actual map of space and stored where things are in that map. And that's why it's super useful to have grid cells and place cells.
And their stored map is a world model.
Yeah, so it's a model of that particular environment. I mean, not the entire world, but yeah, you can definitely call it a world model that's being learned there. It's basically features at locations. So you can use the grid cells um, to kind of tile space and map out space and figure out how movements of the animal translate to movement in that space. And then you can associate features with those locations and places in space, and thereby learn a model of that environment.
Yeah, movement is such an important aspect of intelligence. But another thing that kind of differentiates humans is language, which is central to our collective intelligence and also our social structures. We wouldn't be able to communicate if it wasn't for language, and email. So do you think we're born with like certain linguistic abilities or social predispositions, or if so, how does that shape our understanding of reality?
Yeah, complex question. So, language is kind of a late add-on to those basic capabilities of being able to move around in the world and interact with the world. And it seems to mostly serve the purpose of actually communicating knowledge. So first, we're able to map our environment, and we're able to learn where the food is and where the home is. But then language lets us communicate this knowledge that we figured out to other people in our tribe or our group, and basically communicate that I figured out at this location you can find X, and then I can formulate that in language and tell this to someone else, and that person doesn't have to take that long, windy path searching for it anymore, but can go straight there. And I would say that's the primary purpose of language, to communicate knowledge that we have internally. Um, and in the Thousand Brains theory, which is what my work is based on, a big part of that theory, or a big like basis of that theory, is that in the brain we find this functional unit called the cortical column, or in the neocortex, and it's basically like a little functional unit about the size of a grain of rice, and it has a certain structure. So, for instance, if you take a slice of the neocortex, you see a layered structure of different types of neurons and cells. And that structure is very much the same all across the neocortex. Everywhere, like whether it's the frontal cortex or like the visual cortex, anywhere you find this kind of layered structure. And so the idea is that this basic functional unit, the cortical column, is like a general purpose algorithm that is used for anything that happens in the neocortex, whether it's vision processing, motor cortex, or like higher cognitive functions, like also language. So essentially, that would mean that language processing in the brain works on the exact same principles as everything else that the neocortex models. And if you think of language, it isn't so different from other processes. Like if you read a word, it's like recognizing objects, like you're seeing strokes and you're composing them into letters, and letters are placed relative to each other to form words, and words are placed relative to each other to form sentences. So it's kind of like objects that are made out of features relative to each other, or things relative to each other in a map of an environment. So language can be thought of in the same way as other tasks in the world, and be modeled with the same algorithm that's being used all across the brain.
Is that easier or harder? Because we see language as this kind of abstract phenomenon of, language was evolved from, just gestures to like little grunts to actual words, and then we use the words to abstract meaning. So like if I called something sharp, then I would be able to understand what sharpness is as an abstract concept and then apply that to something else. So we had like a more integrated understanding of that. But if language is just like every other task, does that make your life easier, or that make your life harder in terms of putting that into a machine?
Um, yeah, so many different thoughts on that. First, language isn't like a standalone phenomenon. So it's not like large language models that just learn on language and they start with language and all they ever do is language. Humans first learn about the world, how to interact with it, how to understand objects, how to move in the world. And then when they are actually several years old, that's when they can actually produce like meaningful language and sentences and grammatically correct phrases. So it takes quite a while, and language is kind of one of the last things that's added on. And it's also kind of an add-on if you think in terms of species. It's like we have a very sophisticated language, but most animals don't have such a sophisticated language. Um, so we might actually not be that good at language. That might be why ChatGPT is so impressive to us, because if you have a large function approximator that gets an internet scale data set of language, it can do much better than we can do on this basic algorithm that wasn't originally designed for language. Um, so it's not like it's an easy task or just like anything else, but it's kind of like the last cherry on top that we added to be able to efficiently communicate our knowledge to other people. And we have to rely on this existing algorithm. And if we have machines communicating to each other, they might come up with much more efficient ways to communicate than actually producing words like we do.
Oh,
I'm not
I
sure
want to
if I
double
answered
click
all
on
your
that.
questions,
No,
but
you absolutely did. I want to just touch on that tangent for a second. If machines did come up with a way to communicate that's non-language or not language, what do you think it would be? Like graph structures, or would it be something else?
I mean, with machines, you have a lot more flexibility. Like, for instance, if one machine, or like one model was learned about a certain topic, like let's say you have a domain expert that learned everything about, I don't know, operating a certain machine, you could just make a copy of that. You don't need to have this expert explain
Oh,
everything about what it has just learned to someone else. You can just copy that program. Um, so it's not like a human where you have to actually have children and then they have to start from scratch and they have to learn everything again. So there are much more easier ways to do things in machines.
you make me want to just upload myself into Silicon. It's so much easier. So let's turn to thousand brains theory, which is, central to your work and central to, the podcast we're doing today. So I guess let's just start from the basics. What is the thousand brains theory, and what are we trying to solve with that?
Yeah, so the thousand brains theory is kind of a result of several decades of neuroscience research that has been done largely at Numenta, led by Jeff Hawkins and the team there. And essentially, they've been looking at the neuroscience literature for many, many years and trying to distill down some general principles of how intelligence is implemented in the brain. So if you look at neuroscience researchers, many of them are like focused on one very specific field, and it's if you are an experimentalist, it's really hard to look at the big picture. Each experiment can only test something very specific. But what we've done at Numenta is try to really see the big picture and see the general principles that underlie our intelligence. And that kind of culminated in the Thousand Brains theory. And Jeff Hawkins, the founder of Numenta, published a book on that a couple of years ago called A Thousand Brains, um, which I definitely recommend reading if you're interested in this. I think you actually read it. Um,
Sorry to interrupt you. There's also another book called On Intelligence, I believe was released in
yeah,
2004.
yeah,
That's a
that's also
fantastic one as well. Yeah.
cool. Yeah. Um, but yeah, so the thousand brains theory are several key principles that we think underlies intelligence in the neo and how it's implemented in the neocortex. There's a lot of neuroscience evidence for these, and um, yeah, some of these principles, one I already mentioned, which also coined the term thousand brains, is this general repeatable functional unit, the cortical column. Each of like our brain has about like 150,000 of those, and a lot more than a lot of other mammals. Um, but basically, it's the same key general algorithm repeated many, many times. Um, and yeah, that's the theory that each of these columns is actually a very powerful processing unit and can do a lot on its own, like model complete objects in each of these columns. Um, and that's why we call it the thousand brains theory.
I do want to again double click on that because since we're bringing up the fact that there are 150,000 some odd cortical columns in our brain, if there is like an atomic function, then would elephants or blue whales who have much larger brains be kind of predisposed to higher intelligence? Or is there something unique about the human brain and the way it's interconnected?
Yeah, it's a difficult question to answer. So it's not just about the amount of these columns, but it's probably also about how they're connected to each other. For instance, the human visual system has a much higher depth than like the system of rodents, for instance, where it's not just like having many of these columns next to each other and getting raw sensory input and processing that, but
Mm-hmm.
more of like actually learning compositional structure of the world and having more of these like hierarchically connected levels and being able to represent more compositional structure might be something that gives us this ability to like actually think about very abstract spaces or like decompose tasks in many levels. That might be another key factor here. But yeah, we also just have a lot of these cortical columns. And if you compare, for example, the human neocortex to other mammals, you see it looks a lot more wrinkly because it's like so many of them trying to wrinkle it all into our head. Whereas in others, it's maybe a bit less crowded, so you don't have to like wrinkle this sheet of columns into the head as much.
Yeah, leave it to humans to try to pack more than we're actually capable of. I do want to just slightly push back because I was reading a lot about neuroplasticity and the way that, they were taking rats or mice and they were cutting their brains, just taking a little bit out, and the rats were able to continue traversing the maze and remember until they just took the entire brain out, and obviously the rat couldn't function. And so similarly, there are instances where humans have to cut out half of their brain, but they're still able to function and everything. So how does that work in terms of the cortical columns? Because the cortical columns are a physical thing, but there's something else, maybe neuronally, that's going on. And so I just want
Yeah,
to try to figure that piece out.
yeah, that's actually a great point, and it's actually a great argument for this mechanism because even if you cut out parts of the brain, other parts of the brain can just take over that function because it's this general functional unit. It's not like the part you cut out was specifically designed to process images or what, or to process touch. It's like any other part of the brain can take that over if you route the sensor information there. For example, there have been some really interesting studies where scientists rewired the vision sensors of, I think it was rats, maybe some mammal. They rewired the sensory inputs from one part of the brain to a different part of the brain, and that part of the brain could just learn to interpret those sensory signals, even though it was not originally designed to process vision input. Um, and that's kind of like a very, very strong point for the theory that there's this general unit that basically whatever it learns just depends on what input comes into this system.
Yeah. It, it just makes me wonder, like, since we're figuring out so much about our brain, how much will that impact our ability to create human-like AI? And so I guess that's the next, question, which is how does this thousand brain theory impact our ability to create artificial intelligence? Not in the LLM way, but in the actual 1956 Alan Turing way.
Yeah, I think the Thousand Brains project has a much better shot at creating actual human-like intelligence because current AI works very differently from how our brain works. For instance, one big difference is it often learns from giant static data sets, which is just not how we learn. We learn by sensory-motor interaction. We sense, we move, we sense, we move all the time. We're moving and interacting with the world and testing hypotheses. And the whole reason why we are learning and having intelligence is to move and to act intelligently. Um, and I think the fact that we've studied the brain in such detail and are really basing the system on how the brain works gives us a much better shot at implementing intelligence as we think about naturally, like if you ask people what do you think is intelligent, they would describe what humans can do and what we're good at. And so the brain is the one intelligent system that we know exists. So I think if we want to build an artificial one, it's a really good place to start looking at how the brain does it.
And so this is going to be like a convoluted question to ask, but since we learn in the physical space, we absorb language through sounds and we interact with the environment physically. If we put that same brain, I'll speak loosely, into a machine, how would that machine learn? Because they're not interacting in the same physical sense. They would be interacting in like a digital space or in cyberspace. So, like the learning would be similar, or would it be just totally different?
Yeah, it totally depends on what kind of system you put this into. Like for instance, if you put it into a robot who has actual sensors like cameras and touch sensors, um, it's pretty similar to, you can make it pretty similar to us, where you connect like eye cameras to part of it, and you connect touch sensors to part of it, and you can move limbs or whatever if you have like a humanoid robot. Um, and that that I think you can make a pretty interesting analogy to how we are learning. But like you said, you could also connect it to more abstract applications and spaces like navigating through the internet, for example, following links as the movement there, um, or navigating through some other more conceptual space. Um, and there, it's basically the same concept. It's just movement in a more abstract space. You have different actions that you take, like going down links, and then different sensory inputs, like, I don't know, the different information you sense after you go to a link on a website, for example. So as long as you have movement and you have sensory input and you're moving a sensor through some kind of space in some way, it's you can use the same algorithm for all of it. It doesn't matter if it's actual the same sensors that we have or if it's like non-human sensors like ultrasound or LiDAR, or if it's totally abstract spaces like the internet or cyberspace or whatever.
I don't mean to sound like a crazy scientist right now, but I'm just thinking of, putting in AI, like embodied AI, and putting that into a robot and trying to figure out like the best lenses and the best like sensors for them to touch the world. And then I was like, why don't you just like plug in to your brain and allow it to use your body as its embodied um, vessel? But then you go into an entirely different tangent. I don't know if you have any thoughts on that, but that's that's just where my
Yeah, I
mind
think
goes.
once you get to actual brains, it gets pretty messy. Like your brain is very has a lot of plasticity too, and will adapt and change to the system. And yeah, I probably wouldn't recommend doing that right now, but um, it
She never
would.
said never. You didn't say never. I,
Yeah,
I, I do have because I did skip over something. So when we're saying transfer our intelligence into a machine, we're not talking about whole brain emulation. It's a different process.
yeah, no, we're not talking about that. It's so. What we're doing in the Thousand Brains project is taking these basic principles that we outline in the Thousand Brains theory, and we wrote a framework around that. It's actually open source now. We open sourced it 2 weeks ago, so you can go and check out the code. And the framework consists of these basic repeatable functional units, and then you can plug in any kind of sensor that you like and any kind of motor system that you like. And those repeatable units will just kind of model the sensory motor data that's coming in. But it's not like we're doing any spiking neurons or like we're trying to simulate an entire human brain or something, or trying to replicate recordings from a human brain or something like that. It's more those abstract, fundamental computational principles that we implemented in like a very modular framework. If that makes sense.
No, I mean, we're approaching the boundaries of my understanding of most things, which is why it's fun to talk to you because you're way smarter than me. So if I just stare at you blankly, I promise I'm just processing everything. So
Yeah, yeah. Sorry, I hope it's not
no,
going
no,
into too much depth or
it's great.
too.
It's great. Um, it's one of the things, speaking about the Thousand Brains book and On Intelligence, the two books by Dr. Jeff Hawkins. It's one of the cool things about podcasts is I can actually ask all the questions I had while reading those, where before I had to write them down or just like search them up on my by myself. But it's quite different to actually like interacting with the thought as it's conjured in my head, as it's generated in my head. So that's why I appreciate these. So turning back to the Thousand Brains theory, each cortical column operates independently yet achieves consensus through voting. So what is voting and how is that consensus achieved?
Yeah. So, like I mentioned earlier, each individual cortical column can do a lot on its own, but it needs to move. So you can imagine if if you just have like your fingertip and it's moving over the cup and trying to recognize it. If you just have your fingertip, you need to move across it and cover like a certain area of the cup in order to be like, okay, yeah, this is a cup. Or similarly with vision, it's like looking through a straw and you only see a little excerpt of the world. You need to move around in order to recognize what you're seeing. But we have tons of sensors. Like I can grab this cup with 5 fingers, or I can look at it with my whole visual field. And so that's all those sensors are connected to cortical columns or some those processing units, and all of them are trying to recognize what they are seeing. And then they can use this process that we call voting to come to a consensus much quicker. That's how we can do flash inference. That's how I can look at the cup and I can see it without doing a whole lot of movement, or I can like grab the cup and I can at least tell, okay, this is like a cylindrical object, and then I might need to check out the rim and figure out that it's actually a glass cup. But it makes inference much, much faster. And how it basically works is that each of the processing units that see a small part of the environment have a hypothesis of what they're seeing, or possible objects that they might be sensing, and possible locations that they might be in. And then they can send out those hypotheses. So let's like say I have 5 fingers. Some of them might think I'm on a cup. Some might say they're on a coffee mug, and some might say they're on like a can of beans. But they all get some different input. Like this finger that's on the rim is probably sure that it's not on a can of beans because it's feeling this like pretty distinct rim of the cup, and then the little finger is maybe sensing this little dent in the cup that's um, telling it it's not on a coffee mug because that coffee mug doesn't have those features. And together they can then very quickly figure out which is the object that's consistent with all of their hypotheses. And that's how voting works.
So this is like high level and low level prediction.
Um, in a sense, it's so basically all of these individually make predictions of what they're sensing, and then they are sharing those predictions with each other. Um, and that way kind of narrowing down the possible uh, things that they might be sensing at the moment, if that makes sense.
Is this not terrifying to you, just to take a step back from all of this, like the complexity of our brains and putting that into a machine? Like it's a marvel, no?
Yeah, it's pretty crazy. Like, I mean, I mentioned we open sourced this project recently, and for that we needed to write like documentation and all that. And it's just like so much, so many ideas, so much complexity. And I mean, we tried to break it down to some very key principles, very simplified a lot, um, and try to keep it at some key mechanisms, but it's still like really impressive how the brain figured out these super elegant ways to solve those problems that we have every day. I mean, we have such a varied environment. We can learn about all these new things very quickly. You can get a new phone and be able to use it. And a few years ago, there were no phones, and now your brain knows how to use them after a few minutes. So
Yeah, that's a
It's pretty
really
crazy
good
what we can
point.
do.
Oh, that's a fantastic point. You used a great word, elegant, but is that kind of like the seat of adaptability? Have we found that?
Yeah, yeah, I think this kind of approach of learning and especially structuring knowledge in reference frames, like we talked about in the beginning, like having a map of the environment and a map of objects, um, gives us a lot of flexibility, very fast learning and adaptability and generalization. Like if I have a model of a coffee mug, I can use that model to plan actions or do things that I've never done before, that I never practiced before. Like I would know how to pick up an empty coffee mug using this pencil by putting the pencil through the handle and pulling it up. I don't have to practice that 1,000 of times. I don't even have to watch someone else doing it. I can just figure it out
Like
using my
intuitively.
structured model. Yeah.
Huh.
So uh, having these structured models that were learned by moving through space allows you to adapt very quickly and learn very new tasks very quickly. So I think it's a really key aspect of our intelligence and something that's really lacking in current AI.
I immediately go to how to augment that adaptability because as soon as like it's the human thing. As soon as we understand something, we figure out a way to take advantage of it. And so for me, I want to see if we can find our seat of adaptability. Is there any way for us to enhance it or augment it to make us even more adaptable? Like, I know you've
If
thought about this a little
yeah.
bit.
um, yeah, that's a tough question, I guess. I'm not sure if there's, I mean, if you know about how we do it, you might be able to think about how to make use of this algorithm. It's not like we can fundamentally change this basic mechanism. Um, I don't have any like concrete suggestions on that right now, but it's an interesting question.
Is there any way to genetically modify the size of the cortical columns?
How difficult? Yeah, I'm not sure. I'm definitely
No?
not an expert with
See,
that.
I'm
So
just going crazy scientist right now. I mean, we can turn to open source because that is an interesting decision, and I know that's happened in the last couple of weeks. So what
yeah.
was the decision to go open source, and were there any ethical considerations, any technological considerations? Like what was the process around that?
Yeah. So Numenta has been working pretty openly for a long time and had bigger open source projects before. And we used to upload all our meeting recordings as well. And we kind of stopped doing that a while ago and went a bit into stealth mode and tried out several new ideas. And one of them was this project where we had worked on the thousand brains theory for a while, and now it was like, can we actually build something on this theory? And we tried it out. We started working on this about 3 years ago, and by now we're pretty convinced that it actually works, and we have built something that actually works, and we think this is big and this is the future, and we want to share this with people, and we want this uh, to benefit people as well. So there are several reasons why we decided to make it open source. Um, One is we think this is the future of AI, but if we're a pretty small company and there's no way this would quickly disseminate if we are just working behind this on this behind closed walls and try to grow this with our little team. So we want this to become widespread. We want to incorporate ideas of other people. We're hoping to actually get contributions from other people. So the code is all on GitHub, so people can actually make contributions to the code itself. They can interact with us on a forum and suggest ideas. They can help us write better documentation so that other people can understand this approach better. And we're just hoping that by making this such an open source project, it will accelerate progress on this research as well. Um, I must say, since we made it open source, it's been really fun too. So I'm very happy that we did that because the people who have been interested in it so far are super nice. They're really interested, really positive, and it's just so nice being able to talk with people about this research and interacting with other people who have tons of great other ideas. Um, so that's one thing. Another thing I think is it will make it also safer to do all of this research in the open and have everyone out there being able to scrutinize it and figure out what might be potential problems with this, where might we want to consider certain safety aspects. And I think that's just a lot better if we do it all transparently and people can chime in early while we're still in a research in the research phase of it. Um, and I think it will benefit humanity much more if it is an open source project that anyone can use versus some proprietary software that a big corporation owns. So those are some of the considerations we had. We want this to become a widely used technology, and we wanted to benefit humanity as much as possible. And we think by going open source, that's the best way to be able to achieve that.
But speaking of the big corporation, aren't you afraid that a Meta or a Google might come and steal it and take away all the hard work?
It's not like they are taking away the hard work. It would be great to see them actually using our approach. And we put all the code under an MIT license, which means people can also use it for commercial purposes. Um, I mean, ideally, if they do develop this approach further, they would contribute back to the community and have other people be able to keep using this. There are advancements that they make on it, but it would be great to see big companies like that test this approach on whatever problems they are currently facing. Um, so we don't want to be the only ones who are using this approach. We want to see how it works in industry applications or other people's research. So actually be happy about that.
Yeah, I guess I'm the only paranoid one in this conversation. You're just optimistic and everything, which is great. One thing that I always wonder is that in terms of the thousand brains theory, how does that impact our current and mainstream use of AI? So when people think of artificial intelligence, they immediately go to ChatGPT or Claude or Gemini, text and like um, chat interface, those types of applications. But that's not what we're talking about, or that's not the limit
Yeah.
to what we're talking about. It's much more. So how do we get, or if you can explain like what you're doing and how that is so much bigger than what people are used to right now? Like what will you be able to do?
Yeah. So I think an interesting analogy is when computers were first developed, there were these problems that people found really difficult doing like large numerical operations, doing a bunch of calculations fast. And the first computers filled entire rooms, and it was like a huge feat to get them working. And now we have calculators that cost like $1, and you can do those calculations on those. But we still use calculators and they're still super useful and we still need to do lots of calculations every day. And it made accelerated lots of research progress and made a lot of processes easier to do. So calculators are super valuable. We still use them today, but they are not anymore what we consider like a huge feat or super intelligent or anything like that.
Yeah.
Um, so I think large language models or ChatGPT or deep learning will be a similar thing. They are really good at function approximation and they are really good at learning from large amounts of data. And there are tons of applications where they are very powerful. If you have large amounts of data, internet scale data sets, that's a great approach. If you don't need to extrapolate data, if you just need to interpolate between some data points, that's great. If you need function approximation for protein folding or something like that, it's amazing technology. And I also think that that will stick around. But I don't think it will be thought of as really intelligence in the
Yeah.
future. And I think that's what's going to be the system or the type of system that we are working on, which is systems that actually interact with the world. be it actually the physical world or some virtual environments. But basically sensory motor systems that are intelligent like we are. We are interacting with the world in an intelligent way, and I think those will be the artificial intelligence systems that will be most similar. And today we might think of like robotics as a big application area, but probably in the future there will be tons of other applications that we can't even imagine right now. Same as with computers, where we now can do so many things with computers that originally people who designed them didn't even think about.
Like playing Minecraft.
Yeah.
Um, what one thing is that one thing I really dislike about the field of artificial intelligence as it stands, or I guess the way that people treat the field of AI right now, is that as soon as a new technology comes out, or an iteration of of an LLM comes out, people immediately shout like Terminator and Skynet. And when we're talking about technologies like the one we're discussing on this podcast, where we really believe it will be real intelligence in a machine, that kind of sets everybody in a certain frenzy. They immediately think the singularity is there and Terminator's coming and like world is going to be taken over. And the reason I put it in this way is because I want to manage those fears of like, no, that's not how it works anymore or at all. Like that's just Hollywood mumbo jumbo. Because it
Yeah.
seems like, again, with quantum computers or genetic modification or biotechnology or anything like that, as soon as there are technologies that come out that are at the limits of what people can understand, they immediately go to the world is going to end. And then it takes folks like yourself to be like, no, I understand how it works. That's not what we're building. It's actually going to do
Yeah.
positive things, X, Y, and Z. So it's very frustrating.
Yeah. Yeah, no. I think that's a very good way of putting it. If you understand how it works, it's also much easier to manage those kind of fears. So for instance, the neocortex, which is the part of the brain that we're modeling, it's not the entire part of the brain. It's, I think, like 75% of our brain, and it's like the top structure. But there are tons of like older structures of the brain, the subcortical structures, um, and those are responsible for emotions and basic drives and uh, like controlling bodily functions and all these things. And we're not modeling those parts of the brain. We're modeling the neocortex, which is essentially um, a very sophisticated map of the world. And by having this way of learning a sophisticated map of the world, the user can then use that map for whatever purposes, like a very powerful uh, computer that you can tell what to do, and the computer will then execute that. But the computer doesn't have any emotions or drives of its own, or won't suddenly start wanting to do something else than what you tell it to do. We're not modeling those parts of the brain that do that. It's basically just learning representations of the world. Um, so that's one aspect of it. Um, Another one is this kind of existential risk fear and the idea that there will be like an intelligence explosion and so on. And there are lots of arguments against that, and you could talk about that for hours as well. Jeff Hawkins in the book writes a lot about that as well. So if someone is really interested on that, they could read up on there. But I don't want to take up the whole podcast with those discussions. But basically, the TLDR would be that we're not worried about those things because that's just not how the system works or what could happen with this kind of system.
Absolutely. TLDR, we're good. Don't worry about that. Focus on other
Yeah.
things. The last two questions, I've really enjoyed this first conversation officially. So, what advice would you have for young people that want to get into this space? Maybe not just AI, but technology in general. Young people who are in high school or graduating college or university that are interested in, pursuing these deep tech ideas, but without really general direction. What would you say to them?
Good question. Yeah. I think it of course depends a lot on what this person's interests are. What I always find what I find really cool nowadays is that you can learn about basically everything online pretty quickly. I mean, you can even just go to ChatGPT and ask it about a topic. There are so many online resources like videos and tutorials and all that on any kind of topic. Um, and I guess one thing I find always useful is like really jump in and get your hands dirty and try to implement a project yourself. So not just going on YouTube and watching a bunch of videos, but instead like actually thinking about little toy problem to start with that you want to implement and then just getting started and then using Google, ChatGPT, whatever you need to figure out the ropes. And I always learn the best by doing, and that's kind of the approach I usually take. Um, but yeah, of course, that really depends on the specific topic. But yeah, I mean, the world is changing so fast nowadays. It's like the time where you actually have the time to read several textbooks on a topic. Uh, by then, that topic is often outdated already. So
Yeah.
I feel like just kind of going in and starting to work on something and trying to draw from whatever you need to solve that problem gives like the quickest intro to a topic.
Yeah, absolutely. I mean, YouTube has so many free resources. You could probably get yourself to 60 to 75% proficiency in any given topic just through YouTube.
Yeah,
One thing I always enjoyed about Jason Calacanis and Lex Friedman's podcast together is that Jason Calacanis, who's an angel investor, he's like, Game of Thrones and Breaking Bad, the TV shows, they're like 200 hours each. So why don't you not watch the next two TV shows and put all of that time to learning, how artificial intelligence works or anything else, like don't
yeah.
waste your time streaming TV shows, spend your time doing something productive. Just as a follow-up question, what technologies are you interested in, like deep tech or anything else other than AI?
I'm mostly uh, focused on whatever is related to my work right now because I also have a little baby, so there isn't a whole
Oh,
lot of
nice.
time
Congrats. Sure,
outside
sure.
of that left anymore.
Yeah.
But yeah, I mean, I find new technologies pretty exciting too, but just the past year hasn't been a lot of time to dive deep into any of that.
No problem. No problem. Yeah, baby comes first, as always. Um,
Yeah.
as a final question, I always like to ask, if you had a magic wand and you could solve one problem in the world, what would it be and why? It doesn't have to be related to your work or to artificial intelligence.
Okay. Yeah, the last time we spoke, you asked me that question, and I
I don't know what you're talking about.
had to think a moment, and unfortunately, I didn't spend a whole lot of time thinking deeper about it afterwards. Otherwise, I would be more prepared now. But I think I still like my original answer. Um, if I mean, this is not a realistic answer, so, but just if I did have a magic wand, I would probably spend it on uh, relieving human suffering. Uh, if it can't be done on like a more general scale, then probably something like cure like diseases or something like that. Um, I think that would be a good one.
Oh, I mean, it seems like you're on the path to doing that with Numenta and the Thousand Brains theory. When you guys are successful, it'll just be a couple more steps to achieving that. So I just want to
Hopefully, yeah.
thank you, Dr. Clay, for being here for an unofficial second time, official first time. Where can we find you online?
Yeah, if you just Google Viviane Clay, I think I should pop up. And then also if you go to numenta.com or to thousandbrains.org, um, both of those websites contain like all our projects links if you're interested in the project or to learn more about Thousand Brains theory. And there will also be links to myself as well, if that's any interesting.
It's absolutely interesting. And also, I would definitely recommend reading On Intelligence and A Thousand Brains Theory by Dr. Jeff Hawkins, because those are fantastic books. And there's so much
Sure.
more than what we talked about in this podcast.
Yeah.
So 100%.
Yeah, there's
Dr. Clay,
tons more. And we also have a YouTube channel now that we talked about. You are able to learn almost anything on YouTube. But we have a YouTube channel called Thousand Brains Project, and there we upload all our meeting recordings. We also have some more condensed videos, like a quick start playlist to kind of get an overview of the project. And just yesterday we had a launch symposium where we gave a high-level overview of the whole project and our approach and the implementation. And we uploaded the recording of that today as well. So that would be also a great introduction to the project.
fantastic. I look forward to reviewing all of those. Dr. Clay, thank you so much.
Yeah, thank you.